All right, so now that we've seen the definition of a double integral and done some things with it, let's look at some properties of what a double integral satisfies. All right, so the first thing is, this is kind of what we use to define it, is if f of xy is always greater than or equal to 0, right, then the number given by integrating the function over a rectangle, right, this is the volume right, so this is the volume under f of xy, and, well, under not just f of xy, but the graph of it, so z equals f of xy. So the volume under z equals f of xy, and above the rectangle R. The rectangle R. Okay? So, and that was exactly what it was for a single variable. If the function f of x is always greater than or equal to 0, then integrating it over some interval gave the area under the function. In this case, it's sort of the volume under the function. Right? And then there's some other things that you might remember using for single integrals that are still true here. So if we do a double integral of f of xy plus g of xy dA, all right, we can just split that into two as double integral over R f of xy dA plus double integral over R of g of xy dA. Right? Just like what happened before with single variable integrals. Right? Well, if that's true, you might ask, what happens if I multiply the function by a constant? Do you remember what you could do before? Just factor the constant out. And that works here too. So C R f of xy dA. All right? And then the last property we could ask about, and this, oops, 3 doesn't normally come after 3, does it? The last property we could ask about is if we're comparing two functions, can we compare their integrals? So if f of xy is always less than or equal to g of xy, then how does the double integral over R of f of xy dA compare to the double integral over R of g of xy dA? How do these two compare to each other? Well, if f is always smaller, then you might guess that this is also true, right? So these are just some quick properties of the double integral. All right?